Well, thank you for taking the time out to join. I joined ARPA-E about 8 months ago, and I'm trying to start a program on high-performance insulated glazings. So before we get into that, however, thought I would give a brief introduction to ARPA-E. ARPA-E stands for Advanced Research Projects Agency for Energy. We were modeled on DARPA, which was formed after the Sputnik launch in the late 50s. We were formed in 2007. First awards were given out in 2009. And as of 2021, we've given out about over 1,400 awards, 69 plus programs in various areas. Current funding is about 470 million. That was last year. This year is about the same. Typical projects range in size from 500,000 to 5 million. There's also scale up, which is a little bit more, but the typical programs are in that range. So, what is ARPA-E all about? Well, we want to look at transformative research here, and if you look at the cost per performance, existing technologies will follow a slow trend downward with time. ARPA-E is looking at transformative research that is much higher cost, but potentially disruptive to this existing technology curve. So our model is to develop programs which have multiple teams. We realize that a lot of these teams will not succeed, which is the high risk part. But the hope is that with these many shots on goal, one or a few of these teams will be able to develop technology that will rapidly decrease the cost of these high impact technologies. So we look at two aspects. What is the problem to be solved and whether it has an impact? So if we look at this graph here of technology difficulty versus impact, we are not interested in science projects where the technology may be difficult, but doesn't have an impact in the real world, right? We want to look at high impact, difficult ARPA-E hard research. So this is the area that we are interested in working in. We don't do incremental research. Okay? We want revolutionary, we want hard targets. We provide the funding for teams to reach that, and etc. So let me go over some terminology on Windows before we get into the programmatic aspects. We're looking at an insulated glass unit, or an IGU. An insulated glass unit is two or more panes of glass that provide a measure of thermal insulation. A single pane window is not an IGU, okay? So this is a typical dual pane construction. You have two sheets of glass separated by a spacer containing a desiccant, and you have this synthetic rubber on the outside to provide a gas and moisture barrier. This is a double E. This is essentially what this is. There are thin triples, there's aerogels, and there's vacuum insulated glazings. And these are all examples of IGUs. If you look at a typical double pane window, you have an IGU that goes into a sash. And in this double pane window, you have two of these IGU sash units that go up and down within a frame. And this frame plugs a hole in your wall. The focus of this research is on IGU development only. It's best if you have an IGU paired with a thermally insulating sash and a good frame, but the sash and the frame are out of scope of this program. Okay, we want to focus on the IGU instead. So if we look at a typical double pane IGU, you have two sheets of glass and a gas layer in between. The radiation across this gap is controlled using a low emissivity coating. It can be a hard coat or better, a soft coat, which can have emissivities as low as 0.02, and that essentially kills the radiation across the gap. You still have convection across the gap and conduction, and this window performance is given by an R value or a U value. These are just inverses of each other. This 5.7 is to convert English units to SI. The R value can be center of glass value or the whole window value. Okay, we'll distinguish which ones we're talking about here. So if we wanted to reduce the heat transfer in an IGU, okay, a typical double E low E with air will be about maybe R2. If you replace the air with argon, which is 1% of the Earth's atmosphere, you can get better performance. If you replace it with krypton, you can get even better performance because it's lower thermal conductivity and higher density and higher viscosity. Krypton is 1 part per million in the Earth's atmosphere, so it's very expensive. But you can replace the gas to do this. You can always add another layer of gas and glass onto this, triple low E. In this case here, you're making it thicker though, heavier. You have 1.5 times the material costs, et cetera. Triple panes are available today. They're about 2% of the market. They're not really adopted. You can have a thin triple in which you've taken essentially this double low E glass and put a very thin layer of glass, 0.5 millimeters to 1 millimeter within this gap. And that cuts down on the convection within this these two gas layers, and it's more of a pure conduction, and you can increase the R value that way. You could replace part or all of this gas with an aerogel. An aerogel, typically these days has about a half the thermal conductivity of air, and it also helps to cut down the convection within this gap itself. And last, there's the vacuum insulated glazings or VIGs. And in this case here, we've gotten rid of all the gas, okay? So why are we interested in doing this? What are the potential energy savings for the United States? Well, the US uses about 100 quads of energy a year for all purposes. And about 35% of this energy is used in buildings. And of this 35 quads, about 35% of that is used in the HVAC system for heating and cooling. And roughly 30% of that heat through the envelope goes out of windows. So we have 3.6 quads of energy going out of windows. Let's say there roughly are 3 windows on average across the United States. If we were able to replace all of them with, let's say, an R10 window, then we could save 2.4 quads of energy. It's a huge amount of energy savings. So the potential program vision statement is, how can we make the whole window R10? How can we make that the default choice for retrofit and new construction so that we can save approximately 2.4 quads of energy? The technology that we're using today, this low E IGU technology, is 50 years old. And we've learned a lot since then. So the question is, how can we make this infrared image of a house in winter, which shows that even though the windows are a small fraction of the overall surface area, there's a lot of heat flowing out of those windows. How can we make that look something like this? Okay, so that's the goal of this program. We want the windows to be nearly as insulating as the walls surrounding them, or better than the walls that are surrounding them. So let me talk about the importance of retrofit. Any technology we develop needs to be retrofittable because we have a huge amount of existing buildings that are going to be with us for a very long time. In 2021, there were only about 1.5% of the buildings that were new, okay? The rest have been there. So in order for us to have an impact, we need to have low-cost, retrofittable, highly insulating windows. And if we have this, we can reduce energy costs for consumers. We can decrease the cost of the heat pumps that are required. We can reduce the grid, the load on the grid, and we can reduce CO2 emissions. So what does it take to go from where we are today? The best ones now are probably, this Energy Star 7.0 came out a couple of years ago. and they're specifying R windows between R3.1 and 4.5, depending on the geography. But let's say we want to get to much higher insulating windows. How do we do that? Well, unfortunately, in the US, energy is cheap. And so the only way to really get to this level is to either provide incentives for people to do this or force them to do it through code changes. But we can't force people to adopt technology that doesn't exist, or if it's way too expensive. We have to really drive down the cost of this better technology to similar costs of technology today if we want to be able to have a chance to change codes. So this is the current IGU landscape. This is the cost of manufacture versus the R value. A single pane window is about R1 and costs about $1 a square foot. A double E, maybe R3.5 to R4, it may cost about $3.50 a square foot. Triple and quad are thermally much better, but they're heavier, they're thicker, they're not necessarily good for retrofit applications, especially quad windows. Aerogels are somewhere here. I don't know what the cost of manufacture is because you can't buy it now, but they can have, performance comparable to triple panes. And VIGs you can buy today, but they're very expensive. So the goal of this program, potential program, is to reduce the cost of these IGUs so that they have roughly R10 or better performance, and this is the whole window, not the center of class, at a cost that's roughly similar to that of double pane IGUs. Okay, this is what it's going to take in order for this technology to be adopted. So this is a top-down techno-economic analysis for VIGs. And this sort of illustrates the challenges that we face. So this is a plot of the cost of manufacture on the y-axis versus the production rate. And we're assuming that the material costs are the same as for double low E IGUs, and we assume a typical depreciation schedule. So this shows that, if you're 2, 5, 10 million, maybe even 20 million square feet of initial capital investment, you can drive down the cost of manufacture to close to this, to pretty similar levels, as long as you can get your production rate up. Okay, so where are we today for IGUs? Double pane low E IGUs. You can buy a double E low E IGU line for, let's say $5 million. And this IGU line will be able to produce about 2 million square feet a year. On this top axis, if we assume that this 2 million square feet a year is only producing the average window size in the US in an 8-hour shift and 350 days a year, that means one IGU is coming off the line every 39 seconds or so. Okay, so if you want VIGs to be able to compete with double pane low E IGUs, we have to get to sort of these levels. So let's say we have use this double E low E IGU with argon as a baseline. Let's say it's about $3.50 a square foot. And we have a $1 rider above that. And we use this as a target cost. Well, that means if you have a 20 million investment in your initial capital, you have to produce about 2 million square feet a year in order to sell your IGU at $1 above double pane. If you can lower your cost to $10 million, you can probably get by with about 1.2 million. But where is IGU production today? Well, it's sort of up here, okay? It's an order of magnitude larger than what we need to be in inertial capital costs, and the production rate is about an order of magnitude lower than what we need to be if we want to be able to sell it at $1 above double low E. So we need technologies which will increase the rate of production as well as decrease the initial capital cost. Decreasing initial capital costs is also important because the lower the initial capital costs, the more competitors we can bring into the market. Okay, if you had to make a $5 million investment versus a $20 million investment, the $5 million investment is much less risky. And so you'll have a lot more people getting into the space and therefore competing and driving down costs. So what are the technical challenges for VIGs, let's say? We'll talk about VIGs and aerogels, aerogel technologies. So the VIG technical challenges are, this is how a typical VIG is made. You have two sheets of glass. You put these little spacers on to keep them apart when you pull a vacuum. You have to seal the edges, okay? This rigid edge seal here, it's typically been metal or a low temperature melting glass frit. If it's a rigid edge and this experiences thermal expansion and contraction, you have all this thermal expansion stress or contraction stress being applied to the edge seals. So the edge seals have to be very, very strong and tough. Another problem with this rigid edge seal, like in this configuration, is that you have an R1 edge. You have a direct thermal short between the outside and the inside through a layer of glass, and that can result in cold or cold edges and thereby reduce the thermal performance. The vacuum level here within the panes needs to be about a millionth of an Earth's atmosphere in order to get the thermal conductivity of the gas to essentially zero. So during the manufacture of VIGs, what are the challenges? Well, these spaces are, up to 25 to 50 millimeters apart. So you need to place hundreds to thousands of these spacers on a sheet of glass, within, let's say, a minute. That's a challenge. And how do we make and design these spacers so that they can resist stress, they can take the stress and minimize abrasion on the glass itself? And can they also be made with a material that has a lower thermal conductivity than is typically used? So some possible technologies that could be used are perhaps glass printing, or Corning has developed a process where they shine a laser from one side of the glass and it melts the glass on the other side locally and it forms this little bump. That may be a way of rapidly making these little spacers. You also have to have a hermetic edge seal. Okay, the pressure within this between this vacuum layer, it can't go more than 10 to the minus 5 atmospheres. So how do we ensure that it's going to do that for a 50-year life? Okay, and can this thing be made flexible so that it maximizes reliability? So here's a crazy idea that I proposed during my big summit last May. And let's say you had two sheets of glass and you had a small amount of liquid gallium. Well, this liquid gallium will wet glass on both sides. As long as you can keep it from moving around, this would provide a hermetic seal. It's a metal seal. It just happens to be a liquid. And this would also allow these two sheets of glass to expand and contract relative to each other with thermal changes as well. Is there a material that you can extrude on like an epoxy, but is self-curing? Problem with epoxies is they're permeable to gases. So is there a way you can minimize the permeability so that it provides a hermetic seal so it can have a 50-year life? And lastly, we have to pull a vacuum on this. So how can we take care of the water and gas and other organics that are going to come off the surfaces of the glass? We can use getters, but perhaps you can clean the glass beforehand so to minimize the off-gassing like V glass does, or you can use a high-capacity getter. The getters are these reactive metals that chemically react or adsorb the gas and keep it on the surface and prevent it from going into the gas phase again. Aerogels. So what are aerogels? Aerogels are materials that have a huge amount of porosity. The pores in this case are anywhere from, let's say, 2 to 50 nanometers in size. And because of these small pores, they limit the motion of the air molecules, and you can get thermal conductivities of an aerogel that are less than that of air. So this is what aerogels have typically looked like in the past. You make it by putting precursors within a liquid solvent. These precursors link up to form the skeletal structure, and then you have to remove the liquid without collapsing this skeletal structure. And the way that's typically been done is either supercritical extraction or solvent exchange. And you have to remove the liquid, and that leaves a skeletal structure itself. So this aerogels have been used in quite a few applications. Here's just a couple of them. NASA flew this on a spacecraft. They flew it through the tail of a comet, and they used this aerogel to gently decelerate the comet dust particles from a high velocity to essentially zero, so they wouldn't be destroyed, and they could analyze what it was composed of. It's also been used for thermal insulation as well. What are the challenges associated with aerogels? Well, it takes a long time to remove the solvent, hours to days. And again, you have to get the production rate up, okay, if you want to make this cost competitive. The aerogels that are typically made are perhaps 3 to 4 millimeters thick for window applications. In order to get to R10 or above, we need about 18 millimeters. The question is, how can you do that without cracking the aerogels and retaining the clarity and minimizing haze? So these are potential program metrics that we are targeting. We want an R10 or greater value for a 24-inch by 24-inch prototype IGU. Okay, that's the R value that we're targeting. I can tell you now that the VIGs that you find in the market today, all of them will not satisfy this metric, because in this size, you're going to get a lot of edge conduction. Okay, so you have to look at other schemes here. Number two is a cost premium. We want that to be less than $1 a square foot above the IGUs. 3 and 4 are metrics to make sure it's retrofittable. Okay, we want this to be less than 4 pounds per foot squared. And the thickness has to be less than 1 inch. And 5 and 6 are essentially metrics to make sure that it's really a window. Okay, we don't want something that's hazy, that's like a frosty skylight. We don't want any of that. We want it to be nice and clear, and we want to minimize the IGU bezel width. Enroll is developing some enhanced durability evaluations of IGUs, and it's a work in progress, but we want any prototypes to pass this more rigorous Enroll enhanced durability evaluation. So if you look at all these technologies, double OE, triple OE, thin triple OE, VIG, and aerogel, none of them meet the current the performance metrics. None of them meet essentially the cost premiums. Some of these are, maybe suitable for retrofit, and etc. So, okay. So this is a potential program structure. We want people to form teams. I can produce prototype VIGs, aerogels, or any other technology that can satisfy the above metrics. There are people who have component technologies, for example, for VIGs that may go into a subcomponent technology, but we want them to work with teams and be incorporated into teams. So we're going to fund teams directly. We're not going to fund these individual component technologies. Once these are developed, we're going to send it out for testing and certification, thermal testing, as well as enhanced durability testing. And we also want independent evaluation of the processes that are used to develop this, to make sure that the costs are going to be lower than $1 a square foot above the IGU costs. So we want these teams to interact with equipment manufacturers and come up with realistic estimates of what their process is going to be able to do. There was a VIG summit at LBNL, sponsored by the Department of Energy. It was last year in April. We talked about 3 challenges from industry, market, and societal perspective, talked about the market pathways and the research needs for VIGs. Specifically, there were some also aerogel people that had attended. The results of this workshop are summarized in a report that was put out last May. It's freely available for download, and it's a good starting point for those who are sort of starting from ground zero. Last, I wanted to advertise ARPA-E is going to have an industry day at Glass Build America. Glass Build America is the largest glass window and door convention in the United States, in North America. We will be hosting an industry day on October 2nd in conjunction with that. It's the last day of this Glass Build conference. No registration is required. Well, registration is required, but there's no registration fee. And you can also attend this event without attending Glass Build. We'll be providing a program overview. We'll have speakers from DOE. And most importantly, we will provide teaming opportunities for people. Okay, so this is just some additional information on Glass Build. The registration is pretty nominal if you just want to walk the trade show floor, which I would highly recommend because you'll be able to see all this glass equipment and talk to manufacturers, et cetera. So that's pretty much all I had. So I will stop sharing my screen so we can see the Q&A, and I will try to answer questions that people may have. Let's see. So let me see here. What's the first question here? Do you have any metrics that target manufacturing throughput or speed? That's a very good question. It all depends on the initial capital cost. So we saw that if you have a lower initial capital cost and you want to sell for $1 a square foot above double pane low E, you can probably get by with half the production rate of 1 million square feet a year instead of 2 million square feet a year. So we don't. So that throughput is mixed in with the initial capital costs. So you can't answer that alone. We just want to make the final cost $1 above the double pane IGU. Can you share a link to the VIG Summit? You can just type in VIG Summit, I think LBNL May 2024, and you'll be able to find it. Can you share slides? This will be recorded and made on a YouTube video. What's the timing of this potential program and projected award size? Typical awards, I can't say about this award. The timing, we don't know yet. It has to be approved by leadership. I'm guessing, within 6 months or less. The project award size all depends on the proposers, and they went from 500,000 to a few $1 million, I guess. For your program structure, are you seeking proposer teams? Yes. Are you planning to test these in real buildings or a lab? We want these prototypes to pass the NREL enhanced durability standards. So that's what we are looking at. If we can survive that, general feeling is that it should be okay in the real world. Okay. Let's see, could you elaborate a bit more on the ideal team to be structured? Well, you have to be able to, meet all the metrics. So whatever team you put together, we can't advise you on that. Other questions? Are there particular requirements on type of glass used? Is tempered glass required? If you use regular soda lime glass, the spacing between the space, the spacer pitch is going to have to be smaller. So you're going to get more conduction through the VIG itself. So high performance VIGs typically use tempered glass. So you get, you can have lower thermal conduction. What else is there? Sorry. Will other technologies such as electrochromic or thermochromic windows be used? No. The way I view electrochromics and thermochromics is that they're sort of icing on the cake, that you have to have a really good thermally performing IGU first, and then you can add stuff onto that. So I am interested in the IGU first. Okay. And you share the link to the RFP. There is no RFP yet. We will share it when it becomes available. Let's see. What about the combinations? What is that? Oh, let's get to my list. 10% more expensive than high performance double pane. What about the combinations of thin glass units and solutions like aerogel in the middle of a quad? A quad is going to be too thick. So I would think that it's not going to satisfy the metrics. Manufacturing processes of VIGs are highly energy intensive, which may lead to high carbon emissions. They can be, current technologies can be quite energy intensive. I think new technologies could be developed, are available, or could be developed that could greatly reduce that. So, but a metric of embodied carbon is not necessarily going to be a criteria. Quads can be 7/8 inch. Yeah, but well, okay. I'm not going to answer that question. What are the challenges of using liquid gallium in edge seals? I don't know. You guys should figure it out. If you think it's a viable path, then you should go ahead and pursue that. There are challenges, but economic analysis was done with average 7 to 8 feet squared. Many industry reports have higher averages. It's just a typical number that I found somewhere. It depends on whether you're talking residential and commercial windows, I guess. In terms of retrofitting, does it mean we replace the old glass panes by the new VIG, keeping the old sash? Ideally, yes. If you can keep the old sash, it's fine. If you have to replace the what you have in your home now, double pane with another IGU with an appropriate sash, that'd be fine too, as long as it can be retrofit. Will this program only consider projects related to conductive insulation, or will advancements in radiative insulation coupled with conductive insulation also be considered? I'm not sure what is meant by radiative insulation. In a VIG or an aerogel, you want to have a low emissivity coating, which is going to kill the radiation within the gap itself. You can have coatings on either side of the on the outside surfaces of the IGU, but again, that's sort of an enhancement to the base technology. Is there a target size for prototypes? I mentioned 24 inch by 24 inch. 50-year lifetime is extremely challenging. With the window that requires maintenance every 10 to 20 years be within scope? I don't think so. I don't think people want to have to replace their, have a technician come out and replace and do something with their windows every 10 to 20 years. Is development of high-speed manufacturing machines fundable? We'll have to think about that. I think that may be out of scope. I think the potential for the process to be scaled to high speed needs to be there. And that's why we want people to talk with machine developers. But the development of the high-speed machine itself is a little farther on the technology readiness level curve, so probably not. ARPA-E typically funds are 3 to R or TRL level 3 to 6. Okay. The recording of the seminar available online? Yes. And 2, would there be any preference or restrictions for engagement with OEMs depending on their country of origin? We are looking for US manufacturers, primarily US manufacturing base. We have funded foreign entities before, but it has to be, the technology has to be unavailable in the United States. They have much higher standards than domestic manufacturers. Let's see, anything else? Okay. Let's see, are there any other questions that I can answer quickly? Okay, we have 8 more minutes, so I can wait a little longer.
You might want to talk about component technologies.
Yeah, once the FOA comes out, we cannot talk to you all. We're in a silent period. Before the FOA comes out, I would be happy to talk to you all. Just send me an email or contact me somehow. And if you want to talk about technologies that you have, it's not a problem. And I'll also be available at class build, the industry day at class build. Gallium conductivity. The thermal conductivity of gallium is pretty high. It's probably about 20, 15, no, 16 or so. What's a thin layer? And
Thin quads.
Thin quads, yeah. Not sure what you mean by thin quad. You mean 4 layers of glass with thin glass in between that, or 2 big layers with multiple thin layers of glass. Let's say 2 layers of thin glass between them. Again, if you can meet the cost metrics and and the R value and the thickness, etc., that'd be fine. Anything else? Signal Systems has been tested with real-time installations, converting to double pane VSA residence. Let's see. I see this question on Signal Systems. Can you just contact me offline, and I think we can talk about that. 2 standard layers, 2 Gorilla Glass. That's a thin layer of glass. Okay. Far edge 8 at
Teaming.
how do you plan to encourage team formation? So at Industry Day registration, we'll have a question whether you want to be on the teaming list. If you want to be on the teaming list, you should provide us with some capabilities that you have, and we can make that available to the participants of Industry Day. So you can team. We'll also have 1 minute stand-up sessions. People can stand up and describe their interests in technologies and their needs.
Open networking. And a networking session.
Yeah, we'll have networking sessions at Industry Day as well. If you cannot attend Industry Day, it's still okay. We can still put you on a teaming list. Just send me email. Let's see. Triple hybrid VIG IGUs to meet R10B also be acceptable to explore. It's fine, but you have to meet those metrics that we described. We are installing VIGs in 2 different GSA. There are products that can meet this now, but it's growing market demand is a big challenge. How does this program look to grow the market in addition to technology development? Well, we need to, first of all, we have to lower the cost. ARPA-E is not necessarily involved. We're a technology agency. We're not a marketing agency. We feel that if we can lower the costs to be competitive with double pane IGUs, the market will be there. Any other questions? No? Okay. You're welcome, Kyle.
They're vacuum.
My email, just type in my name and ARPA-E. Is there a vacuum lifetime requirements? Do we need to find a way to monitor vacuum levels? You have to show that your sealing mechanism has the permeability required to have 50-year life of a vacuum. Anything else? No? Okay. Got about another minute and a half, so we'll stay on another minute and a half. Will the presentation be sent out? There will be a YouTube video. We'll try and get it as soon as possible. I'm not exactly sure how long that will take. Can you share an email once more? Can you put
Say in the chat.
Oh, it's in the chat, apparently. My email's in the chat. How can a team demonstrate that the cost target can be met? Again, you have to do an analysis of your procedure, the initial equipment costs, estimates, et cetera. And okay, thank you very much. Have a great afternoon or morning. Bye.